Okay, let's start. Yeah, first of all, I checked YouTube, and it seems that the last lectures are still not available, right? So the very last lecture of 22nd November, and also one lecture before, is not yet in the playlist. So I decided to make a possible alternate from your textbooks, which are available here, and also I guess you can find them in internet, right? Sorry?
In watch those videos, so they are not on.
Really? Ah, I see. Wow. Very good. Very good. Okay. Then let me go along the program. So the first question, power series, maybe it's better, right? Power series, Cauchy-Hadamard theorem. Here, of course, you need to give a definition of the power series, right? Also, radius of convergence. In fact, there are two possible ways to define radius of convergence. So let me recall that, so we have the following formula, right? Where we consider such a power series, right? Yeah, and also we have the following properties. So the series 1, so 1 converges absolutely at z modulo z minus a less than r, and 1 diverges at z if modulo z minus a greater than r. So, in fact, there are two ways to define radius of convergence. One way, you define r as a such number that the following two properties are satisfied. After that, you prove that r is indeed given by that formula, which is called Cauchy-Hadamard formula. Another way, like I did in lectures, that is the definition, right? And then this is Cauchy-Hadamard theorem. So if you use something different from lectures, then you should be ready to this alternative, right? But it's, in fact, from my point of view, it is not very important. So if you use a textbook and you define r as such a number that satisfies this property, and then you deduce that this number equals to z given by the Cauchy-Hadamard formula, no problem. It's up to you. But of course, that is what you should know here. Next question. Yeah.
In the first one, only about definition.
Why? The second is theorem. That is an assertion. Or, as I said, the second may be taken as a definition, but then the first is a theorem. So it depends on what you accept as a definition. Okay? In lecture notes, the first was definition, the second was a theorem. It is rather easy, of course, just using Cauchy test for series, right? But nevertheless. The second question is a little bit larger. So, in fact, first double theorem was given as a corollary of Cauchy-Adamar theorem, right? Uniform convergence inside the disk of convergence was a theorem, and second double theorem was another theorem, right? So, in fact, I tried to give references, but it seems if you have another source, not only YouTube, I didn't know that you have another source. But in any case, you can easily find. So I can say, first question is a lecture of 6th of May. So the first question, 6th of May, right? So second question, uniform convergence, first and second double theorems, 12th of May. So the third question, differentiation and integration of power series and Taylor series. So here we have one theorem about differentiation and integration. Both. You can differentiate power series and you obtain power series with the same radius of convergence. That is what you need to know. So you have the same radius of convergence, and moreover, if you differentiate term by term, then the sum of this series coincides with derivative of the original series. So it means you can differentiate power series term by term inside disk of convergence, inside interval of convergence, sorry. Because differentiation and integration, we start with real power series, right? So first theorems were given, the first questions were given in complex plane. After that, we start real. When we are talking about differentiation, then, of course, only real differentiation. So, also here, Taylor series definition is necessary, right? It's good if you understand the difference between Taylor series and power series, right? So, what is Taylor series? If the function has infinitely many derivatives, then you can determine the coefficients, right? That is the definition of coefficients of a Taylor series. So, what is logical dependence between power series and Taylor series? So, that is a power series, right? If you have a function f which has derivatives of arbitrary order at the point A, then you can define numbers Cn by this formula, right? And the power series with those coefficients is called Taylor series of a function, right? But Taylor series need not to converge to the function itself. The example was given, it's rather huge, right? But of course, I will not ask you full details of this example, no, it's too much, right? But you need to know the existence of such an example. To understand that Taylor series need not to be convergent to the function itself, right? I gave you an example of a function such that all those functions is not zero, right? Not identically zero. But all coefficients are zeros, right? So the Taylor series of that function, in fact, function was f of x e to the power minus 1 of x squared, right? And 0 if x is not 0, and 0 if x equals to 0, right? That is the function. So, I proved in full details, in fact, that is 0 for every n, right? And it means that all coefficients, Taylor coefficients, are zeros, right? But definitely the function is 0 only for x equals to 0, right? So Taylor series of that function is identically 0. It doesn't converge to the function itself. But it converges, by the way, right? But to a different function. That is why, yeah. Okay, fourth question. Yeah, so third question was given 13th of May. Fourth question, Taylor's formula with integral form of remainder, 19th of May. That is just one theorem, right? In fact, you can find it in many textbooks, so it doesn't matter where you find the proof. Lectures or not, doesn't matter. What question?
So that function continues?
It has, I proved that this function has infinitely many. You see, because if x tends to 0, then here we have minus infinity, and e to the power minus infinity is 0. And in fact, I proved that all derivatives exist and they are equal to 0. Okay, fifth question. Representations of elementary functions by Taylor series. That is extremely huge question, right? If you will try to consider everything what I gave to you about binomial expansion, then of course it's absolutely impossible. Right? So, in fact, for Russian students, this question is separated into two questions. One is binomial function, another, all other 4 expansions plus sufficient condition for a function to be expanded into Taylor series, right? So, for you, okay, sufficient condition, just you should, it is used everywhere, right? Except for binomial. Binomial expansion uses Taylor formula with integral form of remainder, binomial function, right? And all other expansions, exponent, sine, cosine, and logarithmic function, they use, not logarithmic, logarithm uses binomial, and exponent, sine, and cosine, they use this sufficient condition, right? So you don't need to remember the proof of sufficient condition. That is why it is not, so it is not written clearly, right? It is not mentioned. Hence, you don't need to remember proof. But you need to know, because that is the base of those expansions, right? So if you have a question about representation of elementary functions, then what you have to do? You have to give 5 expansions, right? 5 expansions. And to be able to deduce, okay, good if you are able to use, to refer to sufficient condition and to prove then expansions of exponent, sine, and cosine, right? And of course, if you are able to refer to Taylor with integral formula, and once again, so yeah, it was also 19th of May. But also next lecture was devoted. Next lecture was about special questions for binomial function. Don't try to look. No, binomial expansion, you see. Next lecture, 1 plus x power alpha, binomial expansion, right? For minus 1 between x and 1, that is relatively easy. You refer to Taylor formula with integral form of remainder, and that's almost all, right? But of course, that is for excellent. What I gave to you also at 1, at minus 1. And that is essentially more complicated. I devote next lecture just to look at those endpoints, right? So don't try. Nothing about endpoints. Same for logarithmic. Logarithmic you just use, in fact, with minus 1, that is geometric progression, right? Geometric progression, for geometric progression, you don't need to refer to any integral formula and so on. It's obvious because you can write explicitly partial sums and to deduce the convergence. So for logarithmic function, you don't need to refer to binomial function, but of course, if you prove binomial expansion, then of course you can refer to binomial, if you know it, right? So, of course, the question is rather huge. Oh, by the way, there was a misprint here in exam program, I'm sorry. Representations of elementary functions, not functions. Okay, 6th question. Complex exponential and trigonometric functions. Here it seems that is lecture of 26th of May. As far as I remember, I didn't write anything as a theorem here, right? It was just definition of complex exponential function, definition of trigonometric function, and relations between them. But relations you should prove. It was not a theorem, but nevertheless you have something to prove here. So, relations between complex exponential, properties of complex exponential also were proved. Taylor series for complex exponential, but that is definition. We define complex exponential function with not we define. I defined in terms of e power x times, I remember, times cosine y plus I sine y, and then we expand. Yeah, you're right. But you need to use Taylor expansion to deduce properties of complex exponential function, right? And the relation between complex exponential and complex trigonometric functions. It's impossible without Taylor expansion. Okay, 7th question. Analytic functions, Taylor's theorem for power series. So here, definition of analytic function, right? And Taylor theorem uses a property of double series, right? There was a property of double series which was used in the proof of Taylor theorem. Of course, what was used you don't need to prove. You may refer without proof to that property, but Taylor theorem with proof. Yeah. So, 7th question, that was 7th question, 27th of May. 27th of May. Yeah, okay. And then it seems the part from former semester, which you will repeat again, right? Not again. You didn't, I guess. Or maybe you did look at those lectures before, but I don't believe. Okay, so then we start with this semester, and you see, 8th question. It seems very easy. Cauchy, Bunyakovsky, Schwarz inequality, right? The proof is very short, but once you start to prove the question, what is it, right? What is Euclidean space? What is metric space? Right? So everything what is mentioned in the proof of Cauchy, Bunyakovsky, Schwarz should be known to you. That is why this question is not so short. But of course, you don't need to prove everything like I did during lectures, otherwise it's too much. No properties of in the product, no. Just to know what is in the product, axioms of the inner product, and that. Sorry? Yes, prove. Yes, but too much, I would say. If altogether it's too much, that is why I. Okay, so 8th question. Formally it was 1st of September, right? 1st of September. Next, Minkowski inequality. Here you see practically it was a, how to say, particular case of triangle inequality, right? So you need to prove that indeed for every Euclidean space is a linear normed space. As a consequence, so you have triangle inequality for Rn, that is Minkowski inequality. That is. Yes, otherwise what to prove? Otherwise what to prove? Here nothing to prove. Yeah. Because that is just a particular case. 6th of September. Okay, next question is extremely huge, right? 10th question, closed open set cinematic space, closure interior of a set, closed and open balls, their properties. So, how to answer to this question? You know, there is a lot of lemmas, right? A lot of lemmas here inside. If you know all definitions which are related to this question, and you know, so what is mentioned as a proposition, as an assertion which has to be proved. Properties of closed and open balls, right? There were two theorems. Closed ball is a closed set, open ball is an open set. Just to prove those properties. But of course, all definitions should be given here as well, right? Then it seems not so huge. Okay? So 10th question, it was 8th of September. Okay, 11th question. Properties of the limits of sequences in Rn. You remember it was rather big theorem, right? Properties were given in, some properties for metric spaces, some properties for Euclidean spaces, and so on, right? But all those properties are absolutely necessary, so because that is the main thing in those topics. So that theorem, I understand it's rather huge, but I would not say that the proof is difficult. It's in fact quite natural. If you compare with many other things, then it's essentially simple. Unfortunately, Boltzmann-Weierstrass theorem is also here, right? So altogether, this question is relatively huge, I would say. But what can I do? It was given 13th of September. So. Yeah. So both theorems should be proved. Yeah. 11th, so that was 13th of September. Okay. 12th question, just Cauchy criterion in Rn, right? One theorem. So, of course, definition of Cauchy sequence should be given here, right? And the theorem, so that is rather short. So it was 15th of September. And also on from the same day, closed and compact sets. And not only that question, closed and compact sets. Here we have two theorems, even I wrote to myself numbers, theorems 5 and 6. Theorems 5 and 6. So what is? Theorem 5 says that every closed subset of a compact set is compact, and theorem 6 says that every compact set is closed. Or maybe vice versa, I don't know. No, it's correct? Okay, but doesn't matter. So two theorems, they were together. I don't remember which was first, which was second. Doesn't matter. No. As I said, just two assertions. Every closed set of a compact set should be compact, and every compact set is closed. That's all for this question. Of course, definition of compact set is also necessary. Okay. 14th question, the same lecture, or maybe next one also, right? I think, yeah, proof I didn't finish on that day. Theorem 7, compactness of a cube in Rn, right? That is difficult proof, right? But very important assertion, and not so difficult as implicit mapping theorem, so let it be. As you could observe, no implicit mapping theorem, right? Sorry? Yeah. So, question 15, compactness criteria in Rn. That is 20th September. So, you see, what is compactness criteria? Compact in Rn is equivalent to either closed and bounded, right? Or for every sequence of points in our set, there is a subsequence which converges to a point from our set. That is also called sequential compactness, but I didn't introduce that notion. So, again, proof is not short, but once again, that is very important result. You see, Heine-Borel is not. Heine-Borel is a consequence of compactness of a cube. Yeah. So, yeah, that is a part, in fact. Heine-Borel is a part, either of a cube or 1 and 2, yeah. Okay. Question 16. Heine and Cauchy definitions of limits, the equivalence. Okay, 2 definitions and the theorem, right? I think everything is clear what you should give here. So, question 16, that was also 20th September, right? Question 17. Limits, iterated limits, direction limits of functions in Rn. So many definitions, right? One rather short theorem, and of course the best if you could give examples, which I gave in that lecture. It was 22nd of September. Examples which show that all those things may happen. I mean, iterated limit exists, but usual limit doesn't exist, and vice versa. Limit exists, iterated limits do not exist. The best if you can give the examples. There is a theorem, short theorem, condition, right? But it's rather short. Okay, question 18. Equivalence of 2 definitions of continuity with limits and with preimages. Sometimes it is called topological definition. 27 September. Okay. Again, 2 definitions are given. Theorem is immediately after those 2 definitions, right? I think everything is clear here. Question 19. Weierstrass theorem in Rn. That is also the same day. And here, theorem 2 plus corollary. Because theorem 2 says that continuous image of a compact is compact, right? And of course, traditional Weierstrass theorem, what it says? That every continuous function on a compact is bounded and attains maximum and minimum. And that is a corollary. So don't forget about corollary here, it is very important. Sorry? I said corollary is Weierstrass theorem, and theorem without Weierstrass. But the theorem is necessary, otherwise, yeah. Not only corollary. Okay, Bolzano-Cauchy theorem, that is just theorem, right? It was given just for same day, it seems, right? 27 September. Bolzano-Cauchy theorem. Okay, question 21. Lagrange mean value theorem in Rn. Of course, it would be very good if you could give an example which shows that if you try to generalize Lagrange theorem like it was given for one variable, then it is not true for several variables, right? There was an example for shock. Cosine t, sine t, right? Yeah. which shows that Lagrange theorem, like it was given for one variable, is not valid. But nevertheless, you can formulate and prove something like Lagrange theorem, and it is called Lagrange theorem in Rn. So it was 29 of September. Question 22. The length of a continuously differentiable curve. Okay, here of course you may ask about those things like admissible changes of parameter, right, and so on. So, and also what is difference? So what is curve? So curve, what is curve? That is a mapping from R to Rn together with the set as an image, right? So curve is not only the image, but you need to take into account also the mapping. But then the question of what is admissible change of parameter. Every change of parameter gives another curve, right? But nevertheless, we agree, do not distinguish between curves if they are related by a special way. Which way? So, for example, if we are talking only about curves, that's admissible if this change of parameter is continuous, and inverse is also continuous, and it is strictly monotone, right? So if we are talking about smooth curves, then this change of variables should be differentiable. Derivative is never zero, right? And it's enough to know only about those two particular cases. So if you don't distinguish between two curves, so we don't distinguish two curves if parameters are connected with the help of such a change of such a function, right? Then we think about those two curves as one curve. That is admissible change of parameter, right? After that, we define the length. So the definition is supremum, right? And then there exist two theorems, right? The first, that derivative S prime equals to model of length of R prime, of radius vector, derivative of radius vector of our function, and then that the length equals to the integral of this expression, right? So these are things which are supposed to be answered in that question. So question 22, it was given 4th of October. 23rd question. Second order approximation of a curve in R3. So here you should give that theorem, right? Which includes several definitions, right? Osculating circle, osculating plane, tangent vector, normal vector, right? Curvature, everything is given in that theorem, right? About second approximation. So that is what you should know about the second order approximation of a curve. Okay? Proof is what means vary? Look at the proof of implicit function theory. No, it is not very long. 24. Same. Computation of curvature. It was next theorem, right? Which allows to compute the curvature of a curve. I mean, the theorem about the second order approximation gives you a definition of curvature and gives a possibility to compute if the parameter is natural parameter, length of the curve, right? And if the parameter is another one, just arbitrary, then there is another formula to compute curvature, and it was given in question 24. So no torsion, no evolute, and so on, nothing. Sorry? Binomial? What do you mean binomial? Binomial. Binomial. No. You see, yeah, in fact, for Russian students it is included. But I don't understand why. I mean, from my point of view, if you include binomial, also torsion should be included because they are together, and I don't understand why to include those Frenet vectors and do not include Frenet formulas, but I don't want to make a program which is larger than standard program for Russian students here. So that is why I decided to cancel binomial. So it is not included. Okay, next questions 25 and 26. These are rather short. I mean, not extremely short. Definitions and theorems, rather short theorems. But I mean, here you can use this textbook, right? Integrals along a curve and line integrals. So, question 25, it was 13th of October, 26, 18th of October. So, definitions and theorems, how to compute those integrals. Okay, question 27, area Jordan measure of a subgraph. So you see, in brackets there are words Jordan measure, right? And it means that I would like, in fact, I didn't ask you to learn anything from measure theory, and I spent many lectures about it, right? And I didn't include anything into the program. But you should get some impression about what is it, area or Jordan measure, by yourself, from any source as you want. There are some sources, right? Also, there are Wikipedia and so on, right? So somehow you should give me what is area, right? How you understand the area. Of course, if you follow my lectures about Jordan measure, then I would say how to say what is Jordan measure. You give definition of outer measure, inner measure, and after that you can give the definition of the Jordan measure itself, right? And for outer measure, you don't need to give anything except for, so what is outer measure? Is infimum for all covariance by elementary sets, right? Of volumes. So volume of elementary set is simple, so that is one way to define what is area. From my point of view, it's quite natural, but you see in those books some other understanding is given. Of course, you may follow, but you need to know what is it, right? Sorry? Proof of what? Formula of, you mean for 28? We are talking about 27 for a while. But for 27 there was a theorem, and you see the proof is not complicated from my point of view. I mean, for this theorem, the proof is not complicated. No lemmas, no proof of lemmas. Just refer to lemmas, because everything from Jordan measure theory you don't need to prove. Just refer. So same for question 28. Volume Jordan measure of a body of revolution of a subgraph. It was, so November, 8th of November. So these are only two questions which have some relation to Jordan measure. The probability that you will get it is not very high. Okay, then question 29, differentiability of functions of several variables. Also same date. Necessary and sufficient conditions. You see, you need to give definition of differentiability, right? And also there are two necessary conditions. If function is differentiable, then it is continuous, and if it is differentiable, then there exist partial derivatives, right? So of course you need also to know what is partial derivative, for sure. And there is sufficient condition, right? So if partial derivatives exist and they are continuous, then the function is differentiable. So formally there are three assertions, but the proofs are rather short for two of them. For the very last, not very short, but also not a complicated thing. Okay? Any question? Okay. 30. Multivariate chain rule. Yeah, it seems. Yeah, firstly it was in YouTube wrong date, but now it seems they changed. Now it's okay. It seems official name in English is not multivariate chain rule, somehow different. But you understand what it is about, right? So differentiation of a composition of two. In fact, not mappings. Function and mapping, better to say, right? Because you have mapping and then function. So the terminal usually is the set of real numbers, not a composition of mappings. So that is one theorem, and the proof is not complicated, but of course the best thing, I mean, you should understand also how to write it down with the help of matrices in matrix form. And in fact, from my point of view, it's very difficult to remember without matrices, just by these sums and so on. But with matrices, it's essentially more transparent, I would say. Okay, question 31. I gave you title Independence of Mixed Partial Derivatives on the Order of Differentiation. What is the translation of standard Russian term? But then I understood that standard title is Symmetry of Partial Derivatives in English. It was my mistake also. Do not to check what is standard English title, English name. So that was 15th of November. I gave you only standard condition, which is called also Schwarz condition. There is another one, Young condition, but I didn't give it to you. So for you it's easier than in my standard course for Russian students. Okay, then next question has no, yeah, but you said that you can watch it. So I'm sure it was, which date? 17th of November. Most probably. I couldn't watch by myself because in YouTube is not yet available. Taylor's formula for multivariate functions with Lagrange and Peano forms of remainders. So I didn't know that you can watch. That is why I brought your textbook. It's good, it's good. If you can watch, it's good. Yeah, because otherwise I thought what to do and then to refer, but it will be rather difficult to try to take a textbook to find out pieces of proof to glue them together. It's a rather complicated job, I would say. Because, yeah, for Zorich, the main theorem was Taylor formula with integral form of remainder. And for several variables, I didn't give it to you at all. And then there is a remark that you can change proof a little bit to obtain Lagrange and Peano forms of remainders. Of course, in principle, you can follow, but then you should replace by yourself and so on, right? And here only Lagrange form is given. Peano is not given at all. So that is, if you have a possibility to watch, then of course the best is to use my lectures. Okay, question 33, implicit function theorem. I understand it's quite complicated, maybe the most complicated question, right? And maybe uniqueness. You may forget about uniqueness part. The very last part about uniqueness, that it's unique solution, right? Forget about uniqueness. I mean the proof. In the proof, uniqueness, you don't need to consider uniqueness in the proof. Okay? That is slight simplification, but sorry, it should be asked. So I didn't include implicit mapping theorem, right? But inverse mapping theorem, question 34. Okay, here I have no correspondence because I couldn't watch lectures, so you should find correspondence with the lectures for the last 3 questions by yourself. Inverse mapping theorem, what you have to do here? The theorem itself, right? The proof refers to inverse mapping theorem. So it means the formulation of inverse mapping theorem you have to know. How to formulate inverse mapping theorem, since it is used in the inverse mapping, right? Right? You understand me? Inverse mapping uses implicit mapping theorem, right? Or maybe I called it Different name, yeah, different name, how it was called. Implicit functions given by a system of equations, something like that, right? Just theorem 2 without name. Really? Oh, I don't believe. Some name should be given. But doesn't matter. Yeah. System of implicit function defined by a system of equations, right? That is, or implicit mapping theorem, short name somewhere from those textbooks, Zorich and Friedman. Yeah. Mm-hmm. Yeah, implicit function determined by a system of equations. That is a theorem which is used in inverse mapping theorem, right? Yeah. So you should know the formulation. You use it, but no proof. Reference of the books. For inverse mapping, in fact, in Friedman, it's good. In Friedman inverse, I like how it is given here, but it's practically the same. I mean, inverse mapping theorem is rather simple, right? If it refers to that implicit mapping, or how I called it, implicit functions defined by a system of equations, right? Nothing, just Friedman. It is called, where is it? Yeah, for Friedman. Yeah, inverse mapping, there is a section inverse mapping. Only for two variables. Not good. Only for two variables, it's very simple. In Zorich, I guess it should be. Yeah, in Zorich it is called the inverse function theorem, and it is given, but with words diffeomorphism also. Okay, if you prefer Zorich, you may use Zorich as well. It's, of course, the proof is essentially the same. Essentially the same. It refers to inverse mapping. Okay. In Zorich it is called implicit function theorem. Doesn't matter which setting. With one variable, with one equation, with system of equations. In Zorich it is called, in any case, inverse function theorem. So be careful when you look at in Zorich book. Did I ask about question about reference to book about this? No answer. Okay, question 35. Local extremum of functions of several variables, necessary and sufficient conditions. I think you can find this question in many textbooks. It is an obligatory thing for any book on calculus, for sure. Also, it is here in both textbooks. Question 36. Local extremum with constraints, Lagrange function method. So, sufficient condition without proof. Okay? Do you understand me? So Lagrange function method, you know, there is necessity part, right? So if there is an extremum with constraints, then the related point gives a local extremum of the Lagrange function, right? That is with proof. And sufficient condition, how to determine when you have an extremum with the help of Lagrange function. Only formulation. No proof of sufficiency part. Okay? That's all. So if you have some concrete questions about some places in proofs and so on, then welcome. Please ask me if you have some questions about proofs and so on. Mm-hmm. What?
These properties.
Mm-hmm.
We need to.
That is integral along a curve or line integral. Line integral. Line integral in one. Properties. The value does not depend on admissible parameterization. That is very important property, and you should know it because it's a standard question for Russian-speaking students also. So, but I said everything related to those. These are rather short questions. Why you should cancel something? Wait, that is not line integral. That is integral along the curve. Integral along the curve. Yeah.
Creation and integration of power steps.
Yeah.
You're saying like do we need to show all of them proofs?
Yes, of course. But you see, proof is rather short. So.
Like I still didn't complete this one, but it takes some 2 pages. It's like.
But the proof just a reference to former results, nothing else, right? So, you see, the only thing which you need to prove is that the series has the same radius of convergence. That is the only thing what is really necessary.
And then what we another theorem, we don't need to do this.
No. Especially taking into account that you refer to things from former semester, right? Here. So, and in any case, if you refer to a question from another question of a program, you don't need to prove it. Definitely, if you are talking about some question. Of course, it depends on who is asking you, but I would say, from my point of view, it's not a honest thing to ask. Proofs from other questions different from what is in your ticket. Two questions in one. No problems because no problems since you have written part of exam. No.
We need to do one in this game.
You mean 2 questions? Okay, it depends on what you want. Of course, for excellent, you should try to prove everything, right? But if only about sufficient, then if you are able to prove something, very good. For sufficient, of course, no. We'll see, you see. You have 1 hour to prepare. It's not so short time, I would say. What do you mean?
You said like we have 1 hour.
Yeah. Preparation time. You get your ticket, I don't know, or list of questions, sheet, right? Something like that. And then you have 1 hour to prepare. After that, we are talking. Yeah, in fact, how to organize it, maybe we'll ask you to come to different time. We'll discuss how it's better to do.
In preparation time, you will have access.
No, of course not. Yeah, but that's a different story. No, nothing.
But when we understand, we our example.
Examiners are me and your seminar teacher, Sergei Gorodetsky. He is leaving our institution. That is why he will be not participate. Seems so, yeah. No, he cannot.
Can he choose?
No. If you, because we are only two, what means to choose? It makes no sense. No, two. Gorodetsky, seminar teacher. No. At least as far as I know, maybe something will be changed. I don't know. Yeah, the question about 9 a.m. or not, we'll discuss. If we'll decide to change, for some of you, we'll send emails. Because, yeah, I don't know, 29 person, and most probably not all of you will come, but more than 20 simultaneously, maybe too much. Room is small, yes, you're right. Yeah, most probably we'll separate the time. Yeah. 18, in fact. Yes, so. Sorry? Yeah? Question 5. Yeah? 5 expansions, yes. Main expansions, yeah. Exponent, cosine, sine, binomial, and logarithmic. Yeah. Yeah? What you didn't understand concerning 2022? Change of parameter. You see, because that is the only definition which was not rigorous. What is curve? So curve is the set together with mapping, right? But in general, we do not distinguish between mappings with the same set. When? Two main cases. That is called admissible change of parameter. So for standard curve, if you have continuous change of parameter such that it is strictly monotone, then you don't distinguish between those two curves. If you are talking about smooth curve, then you don't distinguish between parameters, between two curves, if you change parameter with the help of differentiable, strictly monotone function such that derivative is never zero, right? And also, of course, derivative should be continued. Derivative should be continuous, I forget to mention, sorry. Yeah, derivative should be continuous for smooth functions, right? Yeah, that is what I talk.
But for second order approximation of equation R3, I think you said you will not ask this in the exam.
No, about torsion. About torsion, about evolute. I'll not. I said that I'll not ask this in the exam. Yeah, about evolute, about torsion. Yeah, and you see even about binomial, which is included into standard programs here. Okay. Any more questions?
We need 2 questions and we need to prove both, right?
Sorry?
We need two topics and we need to prove both.
Yeah. Most probably you are right. I should split the groups into 2 groups. I don't know somehow how many.
But if you split that into 2 groups, I think it's reusable almost like.
Oh, we can use 2 complex. It's not a problem. Yeah, I think we will do. Maybe some of you will start not at 9 o'clock, but I will send emails, of course. Okay? Any more questions? It seems no. Then good luck. Yeah?
What's the amount of time given to each student to discuss this?
That is. Oh, it was during distant times there were restrictions. Now it's.
Will it be like on the board or on paper?
Oh, of course, you need to write on the paper because of the language. Definitely, the best would be, and of course, for example, I plan to write down my questions by hand. Definitely, otherwise, some misunderstanding may happen. So, definitely, but it will be oral examination nevertheless. I'll write questions.
Because like if we get compactness of Q, then the implicit function.
But you will start your answer and then you will continue the proof. It's not a problem, of course. Not a problem. No. Yeah, I understand, but it is not a good idea to use Blackboard during the exam. Okay, then thanks also.